Hi, everyone. So, in today's lecture, we are going to be looking at artificial light or artificial lighting. And we're really building off that previous lecture where we looked at light and the aspects of light and what we should be looking at for plant growth and development. So, the first question is why should we even consider using artificial light? Right. Well, a big reason is if you are growing indoors, right? If you're growing indoors, artificial light is going to be your main lighting source, right? Obviously, you're going to need it. That's why we should consider it. But even if you're not growing indoors, maybe you're using a greenhouse. If you see on the table on the right there, the depending on the material that is covering your greenhouse, it's going to be blocking some of the light entering, right? And if you look at the all the way on the right there, that is the percentage of light transmittance, and that's the PAR range. Remember that PAR range is our photosynthetic active radiation. It's the wavelengths between 400 and 700 that are really important for plant photosynthesis. And you can see that depending on the material, it is going to be blocking some of that PAR, some of those photons from entering. Now, it's not an extreme amount, right, depending on what you're looking at, but it is blocking some. And again, if we're trying to maximize yield or plant growth, remember what's important. One of the things that's really important is the amount of light, right? Light is what is our plants are using to power photosynthesis, and that's so we need light for photosynthesis, and photosynthesis is creating sugar, and that's ultimately what is growing our plants or ultimately going to increase our yield, right? So you may think about using some supplemental lighting in a greenhouse. It could improve crop quality that I talked about, increase plant growth, and it's probably more important during the fall or winter or spring, right? When not in the summer when you're getting a lot of sunshine, typically in your greenhouse, but in those cloudy days, especially early in the season or late in the season, it might be more beneficial. We can also get some indirect heating from our artificial light. So there's an additional benefit, right? Just like with we want more light. The hotter the temperature, typically the faster our plants grow and develop. And again, this is related to photosynthesis. The enzymes responsible work better or faster under hotter conditions up to a point, about 87, 86 degrees Fahrenheit. And we can also use artificial lighting to extend or manipulate photoperiod. In the last lecture, briefly talked about photoperiod and the importance of it. And we talked about it in reference to cannabis, right? And we said that it is a short day plant. So during it is when we want to switch from it being vegetative, so it's normal vegetative growth, to reproductive, where it's going to start flowering, it responds to changes in day length and particularly shorter days, right? So if you're growing your cannabis plant and you're growing it for vegetative growth, you're going to keep the light on for about 16 to 18 hours a day. And then when we want to switch it to reproductive, we change that amount of light or that day length to 12 hours a day, right? And by shortening the day, it triggers the plant to switch to that reproductive growth and start flowering. And that is true for a number of plants that respond to photoperiodism. Some of them are listed right here. And we have short day plants, right, where when we want to switch them to flowering, we decrease the amount of light or the amount of light per day, right, not the intensity of light. These are short day plants over here, and we have long day plants, which are the opposite, right? We want to trigger them to flower. We want to increase our day length using our lighting, right? So another reason why we may want to look at artificial light. Now, when we're considering artificial lighting, we have four main types: incandescent lights, fluorescent, high intensity discharge, and light emitting diode, right, or LED. So incandescent light, that's like your typical old school light bulb, right? These are rich sources of red light, poor source of blue. And again, we looked at in the last lecture kind of the importance of red light and blue light, right? They both get absorbed by chlorophyll. Both are utilized for photosynthesis. In terms of plant shape, blue light is going to help keep our plants shorter, right? And so they don't get too long or leggy. Incandescent light doesn't have a lot of blue light. A big problem with incandescent light is that they produce a lot of heat, right? So you have to keep them away from plants. If they get too close, we can scald our plants. They're also less efficient than other types of lighting, right? The light bulbs typically last around 1,000 hours. And you can compare that to 10,000 hours for a fluorescent light bulb. Right? So generally, we want to stay away from incandescent light. The next we have fluorescent light, right? This is kind of a step up. It's more efficient than incandescent. It lasts longer, like we just talked about. It doesn't produce as much heat, which is another benefit. And we can also get some in different color spectra, right? So we can have cool white lights, which has a little bit more blue light. Warm white has a little bit more red light. And again, in the last lecture, we looked at the difference or the effects of those different wavelengths or colors of light. So it's a step up from incandescent in terms of growing for our plants or for our indoor growing. The next option is high intensity discharge, and these are, we have two varieties, sodium vapor or high pressure sodium and metal halide. We used high pressure sodium in plant science in those grow tents. That was, we used high pressure sodium lights. So these are even more efficient, right? They're more efficient than incandescent and fluorescent. They're very long lasting, really kind of similar on the low end. They are last as long as certain fluorescent lights. On the high end, they last a lot longer. A downside is that they require extra materials to work, right? They require a ballast to ignite the lamps and regulate voltage. Without that ballast, they can keep on the energy could be too much. I don't know the specifics. I used to at some point, but they can essentially burn out. So you need that ballast to regulate the voltage. I think the voltage just keeps increasing and it'll just burn out. And then the last that we're going to look at are LED lights or light emitting diodes. Now these are really nice. We can, all those little diodes are individual colors, so you can easily change the color spectrum of your lighting system depending on what you want or what you're looking for. They are also really low heat and very energy efficient. In the couple slides we're going to see they're probably the most energy efficient out of all of these. In terms of, and especially in terms of the amount of photons that they produce, and they're also long lasting. So they're kind of the newest one. I think they're probably the most popular nowadays out of all the options. You see a lot of LED lights in a lot of different places. My personal preference as well is LED lights. So, given those options, if you are going to, you're thinking about doing some lighting, either you're going to grow indoors or supplemental lighting, what do you want to look for in your potential lights, right? So probably one of the first things that you want to look at is how much energy or how really how many photons are those lights producing. And again, to look at that, we need to see these values up here. If you recall from last lecture, we talked about that ppf, which is the amount of photons in that PAR range. And again, here's PAR, right? That's the wavelengths from 400 to 700. And that ppf is the amount of photons in that region that are being produced by that light per second. And then ppfd, or photosynthetic photon flux density, is the amount of ppf, so the amount of those photons that are being produced each second that are landing actually on the surface of your plant or whatever surface you are interested in. Okay, so that's really one, especially so if we're looking at these for grow lights, which we are, it's really important that we get these values because they're going to tell us how many photons in that range that's important for photosynthesis, that are important for our plants, are actually going to be landing on our plants. And obviously, in most cases, more photons are better, right? So higher numbers of ppfd are going to be better in general. So that's something you want to look for. The next thing that you want to be looking at is wattage, right? Wattage is the amount of energy used per hour. So this is going to ultimately determine your cost, right? If we look at the average kilowatt hour price in New Jersey is about 1.62 cents, right? So that's the cost for a kilowatt of energy per hour. 1 kilowatt is 1,000 watts. So if we are looking at a light and say it consumes 100 watts, or it has listed 100 watts, that means that it's consuming 100 watts of energy per hour. So if we want to see how much that's going to be in cost, right, we convert our watts to kilowatts. And again, there's 1,000 watts in 1 kilowatt. So we do a little math here, and we see that this light is consuming 0.1 kilowatts an hour. And then we know our average cost is 0.162 per kilowatt hour. So we multiply these together to get an average cost of 0.0162 dollars per hour, right? So pretty cheap. But say, again, you're running this light for 16 hours a day, so you multiply by 16, and then it's about a quarter a day you're spending to run that light. And, it can build up over time, right? A quarter a day, well, over a month, what is that going to be? That's going to be times 30 days on average, about $7, almost $8 that you're going to spend a month with this light. So not a huge cost, but again, if you're buying multiple lights, that can add up. So something to be aware of. You want to make sure you look at the wattage. It's going to help you. Again, if you're trying to assess lighting options, cost is a factor. Efficacy is what we see over here, and that's kind of like efficiency. And this is essentially looking at the amount of photons that are being produced by the light per watt of energy that is being consumed. And if it is written as micromoles per joule, right? If you do a little fancy rearranging of what these things are written as, ppf and watts, and this is what you end up with, micromoles per joule. But essentially, the idea is that the higher number, the better, right? The more photons you're getting per unit of energy. And if you see over here, this is just a quick little example. These are LEDs, so red LEDs, blue, far red, cool white, and this is high pressure sodium. You could see that the LEDs have a much higher number, so they're much more efficient. You're getting many more photons per unit of energy that the light is consuming. So that's another thing that you want to look at. Now, what is nice to give you some a website that will help you in finding these out for different lights is this Design Light Consortium. So they're a nonprofit, and they're looking at energy efficiency. And what's really nice is that they have a database of lights that they have tested, right? So, a manufacturer will say, we do this much ppf or ppfd, and it consumes this much wattage, etc. They actually go and test the lights and give the results for you, which is really nice. I'm going to show you in a second. And one other thing before I do that is these values up here, right? We talked about in the last lecture their definitions nowadays, but you will still see manufacturers kind of use them interchangeably. So sometimes they'll say the par value, and what they're talking about in terms of modern definitions is ppf. Sometimes they'll use ppfd, etc. So just something to be aware of. That these are sometimes used interchangeably, and they can get mixed up. So let's take a look at this Design Light Consortium and see how we could use that to get the information that we're looking at here, or we're trying to look at. So I have it pulled up already. So here's the website. It's designlights.org, and say we are looking at a potential grow light, and I just pulled a random one up on Amazon. This is a Vivosun VS1000. It's an LED grow light. Now, a lot of times they will have the information that we were looking at included, right? So again, we want to know that ppfd value, right? That's that light intensity. If you see here, this has the different ppfd values. This is depending on where that plant would be in relation to the center of the light, right? Or all the different areas. And it has at the height, because again, depending on where you set your light in relation to your plants, that intensity of light is going to be different, right? So if you set this height, if you set this light within 12 inches of the surface of your plants, these are going to be your ppfd values depending on where your plant is in relation to the center of the light. And this is at 14 inches, that's at 18 inches, right? So this gives you really good information. Other things that we wanted to look at, this is the color spectrum right up here. And again, that's falling really nice within that PAR value, right? Your photosynthetic active radiation. It has a nice spike of blue light, it has a good amount of blue light, has a good amount of red light, it includes green as well. So a nice range that we want. I want to see if it has efficiency or that efficacy here. It doesn't have, let's see what it's got. Oh no, that's just a video. It does show it here, right? So here's, it's saying high efficiency. It's 2.75 micromoles per joule. That's pretty good, right? Remember when we said high pressure sodium is 1.7? All those different lights had different values. So this is a pretty good efficacy right here. It's producing a lot of photons per joule of energy. And right down here, it has our watts, right? So 100 watts. So perfect. We did that example. So that's for a light, that's not a lot of wattage. So that's a really energy efficient light. To be able to produce a ppfd value like that is really good. But this is what they're saying, right? So how about, are they lying to us, right? Sometimes what they are reporting may not be accurate. Luckily, we have that design lights that we talked about. And how you can use this is you can just search for different manufacturers, right? So you go to a little search bar. This is a Vivosun. And then over here, you want to look at what type of lighting it is. And this is our horticultural lighting. And then you search. And then it pulls up different options that they have tested. And this is the VS1000. So then we look at the VS1000. It gives you information about the light, which is really nice. It tells you what they report in terms of their efficacy, right? They say 2.64. Their ppf value, right? 245 moles per second. They have the ppf broken down by color, etc. It tells you what their reported voltage range and watts are right there. And then, which is really nice, it tells you what they tested, right? So you can compare what they reported to what they actually tested. And they actually tested really well. I think it's very similar to what is reported. Right, so just it's more information that you can really use to compare these lights. Right, wattage is even a little lower that they tested compared to what was reported. So it's a nice information. Sometimes the light may not include all this reported stuff, and you can just look at what they actually tested. And then another nice thing is they even test the spectral distribution right here. So if you can look, you can see here is our different wavelengths, and that's the intensity. Or what is that? Yeah, so moles per second maybe. I can't really read that too well, but again, look at it's pretty similar to what we saw with that chart. Right, here's our bump of blue light, here's our red light, etc. Here's our wavelength. So good resource for you guys to have if you are investigating different potential grow lights. Okay. So getting back to this, so those are some ways that we can assess our light options. Now, there's going to be instances, or there may be instances, where if it's older lights or lights not designed for horticultural applications, where they don't have that ppfd value, right? And again, that's really what we're looking for, that ppf value. And they will report stuff in lumens or lux or foot candles. And like we talked about in last lecture, that's not the ideal measurement for plant growth, right? That's based on the ability of our eyes to see light, which doesn't really match up with the light that our plants are using, the full range. So it's not ideal. Now, there are some resources that you can use. So if they gave you a lumen value, you can convert lumens to lux, and then you can convert lux over here to ppfd. right? We can give an example of that in a second. You can also convert lux to foot candles as well and convert that. This is as a general, right? This isn't going to be the most accurate. So if you really want accurate values, you either need to see what they are reported or tested, or you test it yourself with a meter, and I'll show that in the next slide. But if you don't have that meter, if you need a rough estimate, you can kind of use this as a guide. So to show you how this works, I think I had it pulled up already, but this is, say you just had something that says it produces, 60,000 lumens. So you can do that, and then if you want to determine lux, you'll say it's 60,000 lumens. And again, this isn't the most accurate because we should have where the distance as well. But then you'll say 60,000 lumens, and I'm shining it in a grow tent, and it's 2 feet by 1 foot, or we'll say 4 feet squared surface area, and then that'll calculate a lux value for you. And then you can take this lux value, and if you want to convert it to ppfd, you take that value, and then you come back over to here, and depending on the source, whether it is a high pressure sodium or cool white fluorescent, you would use that, whatever the conversion factor is, and get your ppfd value. Right, so here's an example. We have a high pressure sodium light that is emitting 60,000 lux at a distance of 1 meter. So that's what it's telling me. And I want to convert that to ppfd to see what, and I'm going to compare that because I want to compare some lights. I would take that 60,000, it's a high pressure sodium, I would multiply that by 0.012 to get the ppfd value, right? So that's an example of one way we can convert lux, if that's all we have, to ppfd. And we're going to see this, actually switch to the next slide. So if we are looking to really measure light intensity, we really want to get a par meter or a quantum meter, because that's going to measure ppfd for us, right? That's really what we want. If we don't have this, we can kind of go around it with some alternative options, but that's going to be the most accurate, right? So if you're really concerned about growing, if you're working in a lab or a greenhouse, or really just your own home operation, and you really want the most accurate information, you want to get one of these meters. Problem is, they're like a couple $100 each, right? So instead of that, if you don't want to spend that, why not have it up there? I'll show you. It's going to be in the attached video in a second. If you don't have that, you can get a lux meter, and that lux meter is going to measure lux, right? And what's nice is it's much cheaper. And then if you have that lux meter, you then can do some conversion, hopefully, to get an idea of this ppfd value. So let's take a look at that video now, where I actually go through some of that work. All right, guys, so this is a digital lux meter, and this is something that we can use to measure light intensity. So as we talked about earlier, ideally we want to be looking at that photosynthetic photon flux density as opposed to lux, right? Because lux relies on lumens, and that is looking at light from our human perception as opposed to what our plant sees. But to get a meter that reads that photosynthetic active radiation, and thus the photosynthetic flux, photon flux density, or that ppfd, to get a meter that reads that, it's going to cost a couple $100 to $1,000, maybe even more. And this guy is about $30. So luckily, what you can do, unless you want very, very accurate results, right? You're working in a lab, maybe you're in a very large operation. For most cases, if you want to get close to what you need, you can just use a lux meter and then use those calculations, use those tables that we looked at in our lab or in our PowerPoint. So I'm going to show how this thing works, and we're going to look at a couple lights that we have set up. Really, really easy. You turn it on. You can switch between lux and foot candles. It also records temperature as well. And there you go. Here's the light sensor right here. See if I cover it up, it goes down. And now all we're doing is we are going to take this and we place it under our light. So I'm going to come in here into our little growth chamber where we have, let's see if I can get that up. Our growth chamber where we have our fast plants going. And I'm going to put it down here, and you can see we're about, I'll put it down to about where your plant level is. If you can read there, it says 912 or 916. It fluctuates a little bit, but you can also see that down in this thing, there's a times 10, and that's important because we're going to add a 0 to this. We're multiplying that number by 10. So we'll say it's about 930 times 10, so 9,300. What's also important is you could see how this number varies by a distance from the source, light source, right? As you get really up close, you can see it gets a lot higher. If I go down here, you see it's really gonna drop. So we have to keep this light pretty close because we need those higher values. So for this example, we're gonna say, see, that's actually a little bit better. We'll say 900, and we'll say 1,000 plus times that 10, so we'll say 10,000. Okay, so that is in our growth chamber for our fast plants. I also have a grow light up over here, an LED light. So let's take a look and see what that is. Ooh, that looks funky on the phone, huh? So that sitting here at about level here is, you can't really read it, but I'll read it off for you. That is about 2,100, but again, that's times 10 because we have that multiplier up there. So that is about 2,100 or 21,000 as opposed to 10,000. And then to compare, this is a cloudy day, cloudy morning outside. We're at about 9,680. And there you could see that times 10 multiplier, right? Okay. Okay, so we have our values listed out here. And then again, this fluorescent light, that is our light that we're using in our fast plants. We have an LED light, that was the grow light. And then we had sunlight outside on this cloudy February day. So what we want to do now is convert these into that PPFD value, photosynthetic photon flux value, because flux density value, because again, that is a more accurate measurement for the light energy that our plants are getting. So we are going to use the table that we had in our PowerPoint and maybe some other resources to get this value, as I'll show you. So if we go back to our table here, we see that we were growing we're using a cool white fluorescent light in our for our fast plants. So we're going to multiply the value we got on our lux by this 0.014 to give us our photons, or really our PPFD value. So we'll go back up to here, times 0.014 equals, and this is going to be PPFD. And then for LED, I realized when I was putting this together that on our chart here, it doesn't list LED. Luckily, there is a website, waveformlighting.com, that allows you, it actually automatically lets you put in values of lux, and it converts this automatically for you. So I was able to use that to get a conversion number for LED, and that comes out to about 0.025. And then sunlight, we go back to here, and our sunlight is 0.019. Oh, there's fluorescent right there. 0.030. Okay, so in this case, this fluorescent is a little bit higher. You can use this measurement. You can go use this waveform lighting if you like, either one. I'll stick with the waveform lighting for now, but I have fluorescent right there. I just did not see it. Anyway, our sunlight is 0.019. Okay. So now let's multiply these all together. I'm going to use the calculator on my phone because I do not want to do that by hand. So the first one, 10,000 times 0.014, and that gives us a photosynthetic photon flux density value of 140. And then this is in micromoles per meter squared per second. And we'll do that with LEDs times 0.025, and that is 525, oops, again, micromole per meter squared per second. And our sunlight, 9680 times 0.019 is around 183.92. Pretty low, right? Again, this is a cloudy day, and it's February, it's winter. So we'd expect it to be low. Okay, so that gives us these ppfd values, and if you remember from our PowerPoint, ideally we want something around 500 or above for our plants that we're looking at. Now, what we can also do is calculate that daily light integral, right? And that is essentially the amount of this ppfd that our plants are getting in 24 hours across the whole day. And our daily light integral is going to equal this ppfd value times the number of hours of light times a value of 0.0036. And that is just the number of minutes in the day, or the number of minutes in an hour times the number of seconds in minutes divided by a million. That allows us to get to the this daily light interval, how we want to have that expressed. So we can do this for all of our plants again, right? So if we're looking at our fluorescent light, and I'll just say our fast plants, it would be our ppfd value, which is 140, times the number of hours in a day, and in this case we have this thing running all day, times 0.0036. And let's do some calculations. I'll do this on my phone real quick. And that is going to equal 12.1, and this is moles meter squared a second. All right, so we have a daily light integral of 12.1 for our fast plants. If we were using that LED grow light that I used to start some plants indoors, we are going to look at our ppfd, which is 525 times, in this case I'll say I'll run it for 12 hours a day, times 0.0036. And let's see what that is going to be. That is 525 times 12 times 0.0036. And that gives us 22.68 moles per meter squared per second. And then we can compare that to what it would be outside. And, we'll say February cloudy. So what you're getting on a cloudy day in mid and February, we have 183.92 times And I looked it up. We have about 11 hours of day length today. And times are 0.0036. So we 183.92 times 11 times 0.0036. And that only gives us about 7.28 moles meter squared a second.